So we are starting on page 412, section 6.1. All right, so we have been doing integration, antiderivatives, which is area under the curve. And so at the very beginning, if you'll think way back when we started doing area under the curve, we broke it up into rectangles. And then we said, well, what would happen if we had an infinite number of rectangles? And that's how we came up with our integration rules. Okay, the limit theory is how we came up with that. Okay, so now we're actually going to look at what happens when we look at two curves. And it's pretty straightforward and it's very intuitive. Because if I were to look at the area between two curves, then I would have to say, well, I'm going to take the top curve in that area, and I'm going to subtract the bottom curve and the area under that. And that would leave me with the area between the curves. Logical, right? And that's exactly how it is set up. If f and g are continuous on the interval AB, and g is smaller than f, keep in mind, it does not matter what variables they give you for the functions. What they're saying is the larger function needs to be on top of the, like, you need to make sure you know which is higher than the other one. And we'll talk about how to do that. Then, if you want to find the area of the region bounded by the graphs, f and g, and the vertical lines that make up the boundaries, then just integrate the subtraction of the two. Take the higher function, subtract the lower function, and integrate that. And then you'll have the area between the curves, all right? So they show this figure here. We have this figure f, we have this function f, this function g. If they want the area between the two, we're gonna have the boundaries there, and we're gonna subtract this function from that function. And they're showing you, you know, in your limit theory, it would have been these rectangles that make up in between is what's actually happening there. Find the area of the region bounded by the graphs y equals x squared plus 2, y equals negative x equals 0, and x equals 1. All right? So while it seems like they've given us four functions, which technically they have given us four boundaries, the x equals 0 and the x equal 1 is just our upper and lower bounds. Okay? So they've really just given us our a and our b, right? The key here is putting them in the right order. You must subtract the bottom graph from the top graph. And it may not always be intuitive. Like here we have a picture. You're most definitely not going to have a picture, okay? So the first thing you're going to know for sure is that we have our A and we have our B from here and here, all right? Now we have to determine, well, which one yields the higher graph and which one yields the lower graph. The best way to figure that out is just to pick a number between your boundaries. So from 0 to 1, I'm going to pick something like 1/2. If I plug 1/2 into this function, I get 2 1/4, right? 2 1/4. If I plug 1/2 into this function, I get negative 1/2. Which one's higher? Well, 2 1/4. That guy goes first. So I'm going to have, this is going to be my first function, x squared plus 2. And then this is going to be my second function, negative x. That's how you figure out which is higher and which is lower. Your higher y, your lower y. And if it's, we're going to do some where it's x equals a function, and it's just the same thing except it's going to be left and right versus up and down. So you just have to make sure you put it in the right order, or you're going to have the wrong answer if you don't put it in the right order. After you do that, just simplify this guy and take the antiderivative. So we have from 0 to 1, x squared. I usually put it in standard order, but it actually does not matter. So we have x squared minus a negative x. Well, that's plus x. We have our plus 2. I'm simply just simplifying it, dx. Take my antiderivative. Antiderivative means add 1 and divide by your new exponent, right? So add 1, my new exponent is cubed, and I'm going to divide by that 3. Add 1, my new exponent is squared. I'm going to divide by that 2. 2, that becomes 2 to the x, and I'm going from 0 to 1. What's nice when my lower boundary is 0 and I have x's in all of them, it kind of zeroes out, right? So plug in my 1, I get 1/3 plus 1/2 plus 2. That's what happens when I plug in 1. Minus 0 plus 0 plus 0. My common denominator here is 6. So this is 2 over 6. This is 3 over 6. This is 12 over 6. So 2 plus 3 plus 12 is 17 over 6, and that is my answer. Find the area of the region bounded by the graphs, and they give us these two graphs. Now, the difference is they didn't give me boundary lines. Here's the thing. When they don't give you boundary lines, then you want to see where they intersect. And then that will give you the points where you're going to figure this out. So if you look at this, we have a parabola pointing down and just a line. Parabola pointing down, line, or the intersecting points tells us our boundaries. So how do I find where they intersect? Well, that is the place where they are equal. Anytime two graphs intersect, the xy value at that point is the same, right? So in order to figure out where they're equal, we set them equal to each other and solve. As simple as that. And so we're going to take my 2 minus my x squared, set it equal to x, and then we're going to solve. Anytime you have an x squared, this is a quadratic. You solve a quadratic by getting it, set it to equal to 0. If it factors, factor it. If you cannot factor it, solve it with a quadratic formula, hence the term quadratic there. But all right, so I move everything to where my x squared is positive. So in this case, I'm going to move everything to this side so that I have x squared plus x minus 2 equals 0. That's how I factor this. I find that easier than a negative in front. All right, so really easy factoring here. My factoring is x plus 2, x minus 1 equals 0, meaning that the two places that these are going to cross is at x equals negative 2 and positive 1. That is my a and b. That's how I solve for a and b. So now that I have my a and b, negative 2, positive 1, I still need to figure out which is on top and which is on bottom. All right? Logic would tell me that if they intersect and it's a parabola, then the parabola is probably on top. In this case, if it's pointing down, if it were pointing up, we would assume that the line was on top. But to double check, you can plug in anything between negative 2 and 0, and 1, 0 is definitely the easiest one to do here. So we have 2 minus 0, that is 2 or 0. That means this guy is bigger. So I'm going to set it up with 2 minus x squared minus x. That is my function here. You can put it in standard form if you want to. It doesn't really matter because you're not really combining anything. Antiderivative, add an exponent and divide by the new one. So we're going to add an exponent, divide by my new one, add an exponent, divide by my new one. We're going to do that from negative 2 to 1. And then we just plug it in. When I plug in a 1, I get 2 minus 1/3 minus 1/2. When I plug in a -2, I get -4 minus -8/3 minus 4/2 or 2. I'll just do a 2 there because that makes life easier. My common denominator here is 6. This must reduce. All right, so we would say this is 12/6. This is 2/6. This is 3/6. So we have 12 minus 2 minus 3. And then we have over 6. This is -24/6. This is positive 16/6. And this is 12/6. So -24 plus 16 minus 12. What, -20/6? So minus a -20 is plus 20. 27/6. Divide by 3, we get 9/2. That is my answer. For sine and cosine, if you set them equal to each other, you have sine of x equals cosine of x. That's what they're giving us. They're giving us the sine and cosine. If I divide both sides by cosine, I get sine of x over cosine of x equals 1. What is sine over cosine? Tangent. Tangent of x equals 1. That happens at your first quadrant and third quadrant, 45-degree angles. So that's going to happen at pi over 4 and at 5 pi over 4. It would be -1 at second and fourth. So that's my boundaries. I'm going to go from pi over 4 to 5 pi over 4. And I'm going to say sine. Sine is my higher graph here, by the way. over minus cosine. Antiderivative of sine and cosine is rather simple. The antiderivative of sine is negative cosine. The antiderivative of cosine is sine. This is going to be some square root of 2 over 2's, right? That's nice about this one. So 5 pi over 4, that's in my third quadrant. They're both negative. So negative square root of 2 over 2 minus negative square root of 2 over 2 is what happens when I plug in 5 pi over 4. When I plug in pi over 4, I just get square root of 2 over 2. So square root of 2 over 2 minus square root of 2 over 2. You end up with minus a negative. So this becomes 2 square root of 2 over 2 minus a negative 2 square root of 2 over 2. Those 2's cancel. And then you have square root of 2 plus square root of 2, which is just 2 square root of 2. Basically, it's the same thing, but just with all your good unit circle.
How did you know sine
Goodness.
was